The rest of this section will involve taking what we've learned geometrically about vectors and using that information to solve application problems. There's going to be three types of application problems we're going to look at. There's general force problems, then we're going to look at incline problems, and then lastly we will do navigation problems using vectors. Okay, we've done some navigation problems with bearing and that type of stuff before, but now we're going to do it with vectors. Okay, so let's start with the general force problems. So what you need to know is inside the box, you will see newtons mentioned. Basically, a newton is a unit of force that equals 0.225 pounds. Okay, so it's a unit of force. It's a way of measuring force. Okay, the other bullet point says sometimes it is necessary to find a vector that will counterbalance the resultant. This opposite vector is the equilibrant. That is the equilibrant of vector u is the opposite vector negative u. Okay, so if you see that word equilibrant, it just means the opposite vector. Okay, so let's take a look at example 6. So example 6 says two forces of 32 and 48 newtons act on a point in the plane. If the angle between the two forces is 76 degrees, find the magnitude of the resultant force. Round to the nearest newton. All right, so it really does help with any word problem to draw it out. So, we're going to go ahead and say there's some object. Okay, so the object here is the point. Okay, so it says, two forces act on a point or object or whatever. Okay, so here is that point. Okay, maybe think of it, try to put it in some kind of context in your own mind. This might be a car, and like this is the scene of a car accident as it's happening. So this might be the car, and then the car is hit by two other cars, and so those are forces acting on that one car. Okay, so try to put it in some kind of context just to help yourself better understand the problem. Okay, so here's the point. If we're thinking of it as a car, great. If not, whatever. But at this point, you've got two forces acting on this point. Okay, so a force is a vector. So it's going to have a magnitude and it's going to have a direction. Okay, so we know we have the two forces. One is 32 newtons, the other one is 48. And we know that the angle between them is 76 degrees. Okay, so we're going to try to draw that out. Let me move this point down. Okay, so say this is the point or car or whatever. So I'm going to draw the first vector. Okay, actually I'm going to go ahead and draw both of them, and I'm going to draw them so that I have approximately a 76-degree angle between these two vectors. Okay, so I'll put one in, I don't know, we'll say, here we go. Let me just draw, and then I'll talk about how I drew it. Okay, let's say maybe there, and then maybe here, like this. Okay, so let me do it that way. Okay, so the point is the object or the car or whatever you want it to represent. And, think of like if this were the car, it's being struck by these forces. Okay, so one force is going to be 32 newtons, and that's usually just a capital N. Okay, and it's acting, when it hits the car, it's acting in this direction. Okay, so that's my first vector. And notice this is the shorter vector. Okay, remember the length of the vector represents its magnitude. So the 48 vector should be longer. Okay, so maybe some other car hit the original car from this angle. Okay, so like this is going to be a force going in this direction. So this is going to be 48 newtons. Okay, and then the angle between these two vectors is going to be 76 degrees. Okay, so this is what this situation looks like. Okay, you've got a point, some kind of object, you've got two forces acting on it simultaneously, and these vectors are acting, or these forces are, coming together at an angle of 76 degrees. Okay, so what we're asked to find here is the magnitude of the resultant force. Okay, as soon as you see this word resultant, it means add the vectors. Okay, so that's what we're going to do here. Okay, we're going to add. So the illustration really helps here. So what I'm going to do is draw in the resultant, and then we'll talk about how to calculate it, okay? Because of the way that I have this drawn out, when we're adding two vectors, it looks like method 2 is going to be preferable here because I can just add in the parallel sides to get my parallelogram, and then I can draw in my resultant, okay? So that's what I'm going to do here. I'm going to form the parallelogram. Okay, so I'm going to draw in the side opposite to the 32 Newton force. Okay, so that's going to be that. And then I'm going to draw in the side parallel to the 48 Newton force. Okay, and I'm just eyeballing this so it's not perfect. So it's going to look something like this. Let me go up a little bit more on this one to make the parallelogram. Okay, so it's going to look something like this. Okay, let me cut this little tip off. Okay, so here is our parallelogram. And to draw in the resultant, now that I have the parallelogram, okay, remember with the parallelogram method, the reason I chose this method is because you have to have the vectors sharing the same initial point. So that's how I already had it set up. So that's why I chose to go this route. So to draw in the resultant, which I will put in red, the initial point of the resultant will coincide with the initial point of the two original vectors, and we will draw the diagonal across the parallelogram to the opposite side. Okay, so this is the resultant. Okay, we always put the arrowhead on the terminal point. Okay, so this is the resultant that we're trying to find. And what we want here is the magnitude. Okay, we do not actually learn the formula for the magnitude of a resultant force, or sorry, we don't actually learn the formula for the resultant of any vector until the next section, but we can still get it here. Okay, so here is our lovely picture. Okay, and we're just trying to find the magnitude, not the direction, so just the magnitude of this particular vector. Okay, so here's a couple of things you need to remind yourself of from geometry. Okay, if you are dealing with a four-sided object, okay, so like a square or a rectangle or a parallelogram like you have here, there are 360 degrees inside. Okay, so you know when we did triangles, we know that the angles inside of a triangle have to add up to 180 degrees. Well, for a four-sided object, that number is 360. Okay, so all angles inside the parallelogram, because it's a four-sided object, they have to add up to 360. Okay, so when we look at this, okay, what's going on here, the way parallelograms work, see this 76-degree angle? If you go straight across to this angle is also going to be 76 degrees. And so that means that we can go ahead and take 360 total degrees and take out the two 76s, okay, and that's what's left for the other two angles. Okay, so there's 180 degrees. Oops, I did the wrong thing. I meant to put 360 minus 76 minus 76. So that means there's 208 degrees left to split between these two remaining angles. Okay, now notice this angle, like I said, the 76-degree angle is going to be equal to this 76-degree angle. Okay, by nature of a parallelogram, the opposite angles are equal. Okay, so I'm going to put that as another tidbit. Opposite angles are equal. Okay, so that means this angle is going to be opposite this angle, and they're going to be equal. Okay, so if I take the 208 remaining degrees and I divide that by 2, that means that each of those green angles is going to be 104 degrees. Okay. All right. So what else do we know? Well, we know all four sides of the parallelogram, okay, because it's like, opposites match. Okay, so if you look where my cursor is, since this side has a magnitude or length of 32, that means the side opposite it will also have that same magnitude. And then down here, this east-west line, it's got a magnitude of 48 newtons. So this east-west line up here will have that same magnitude. Okay, opposites match in the parallelogram. Okay, so we have that. Okay, and when you look at this, okay, again, we're trying to find the length of that red line, okay, but we've got a triangle here. Let's look at this yellow triangle. You could also look at the bottom triangle. I just picked the top one. But this is an oblique triangle. There is no right angle, but we do know side, angle, side. Okay, so this is a SAS case, and so we can use the law of sines, or sorry, the law of cosines. SAS is a law of cosines problem. We can use the law of cosines to figure out the magnitude of this red resultant. Okay, so let's go ahead and put some letters on here. Let's say this is A, this is B, this is C. And so if I draw across and label my sides here, this is going to be side B, this is going to be side A, this is going to be side C. So I am actually looking for side B here. Okay, so which version of the law of cosines are we going to use? Well, since we're solving for b squared, or sorry, since we're solving for b, we're going to use this version where you solve for b squared. Okay, so this is going to be a squared plus c squared minus 2 times a times c times the cosine of angle b. Okay, that's what we need to plug into. Okay, and then that will pretty much give us the resultant force. Okay, so let's plug into this. We don't know what b is, so we're just going to leave b squared as b squared, but side A is going to be 48, so we're going to have 48 squared plus c squared. That's going to be 32 squared minus 2 times A times C times the cosine of angle B, okay, which is 104 degrees. Okay, so we should be able to pop this into a calculator, and that's going to give us b squared. Okay, so let's go ahead and do that. Make sure your calculator is in degrees. So here we go. We're going to have 48 squared plus 32 squared minus 2 times 48 times 32 times the cosine of 104. Okay, so let me go ahead and write that decimal down. So 4,071.184,063. Okay, so if we want b, we need to take the square root. You only need to worry about the positive version because we're finding a distance here. You don't have to worry about this is going to be a force. Okay, so if we're talking about the magnitude, you don't have to incorporate the direction. Okay, so if we go ahead and take the square root here, here's going to be our b value. Okay, so let me write this down. This is 63.8058, and then 3095. Okay, so that is the magnitude. We need to round to the nearest Newton. Okay, so this is going to be, if we look at it, there is an 8 after the decimal point, so we need to bump up to 64. Okay, so the resultant force here is approximately 64 newtons. Okay, and that is the answer that we're looking for. Okay, so that's how you needed to work this problem. Okay, you really need to draw it out. Okay, it's essential. Okay, once you drew it out, it became obvious that this was a side angle side problem and you needed to use the law of cosines. Okay, so let's try another one.